lecture series. Let me quickly go slides over here. So about today's event, we'll be talking about life and work of Professor Butler Lampson, and Dr. Neeran Karnik is going to be talking about him. We'll have that as a first session, or it will be a tea break, and then we'll be experience sharing session by Dr. Basant Rajan and Abhay Gaisas. Quick roundup of today's event. It's being live telecast at Nagpur, Hyderabad, Goa, as well as we have one college, MIT College in Aurangabad. I guess if you want to ask questions, I think so we'll have a dedicated slot at the end of the lecture where people can raise their arms and ask questions. Turing lecture series, as you already know about it, first Saturday of every month, at least till June 2013. Again, the idea over here is to cover contributions of Turing Award recipients, they being the primary research work done in the computer science. So that's the plan for next 12 months, but we are again, if anybody wants to meet, we are all open to continuing this beyond June as well, but definitely till June. Next lecture is going to be on Saturday, December 8th. It's going to be about contributions made by Professor Julia Pearl around probabilistic and causal reasoning, and I'm going to be talking about him that's 2 weeks from now. On Saturday, January 5th, we'll talk about contributions made by Jim Gray, and Anand is going to be talking about Abhijit Vichar is going to talk about John Backus and his contributions on February 2nd. On Saturday, we'll cover the contributions made by Ken Thompson and Dennis Ritchie around Unix operating system. Vijay is going to be talking about him, that's on March 2nd. April 6th, the RSA trio will talk about cryptography and the contributions there. That's April 6th. May 4th, Barbara Liskov, and essentially contributions on distributed computing and fault tolerance. Ajay from Persistent will talk about her. And then Fran Allen, Hemant is going to talk about her on June 1, 2013. Again, if you want to know more about all the Turing Award recipients and their lectures, you can go to this website. It's actually a very good website. They have lectures, papers, their contributions, interviews, a lot of good materials available about all Turing Award recipients over here. We had this semicolons programming contest on 11th August. This is again part of the Turing Centennial events at Persistent. We also had iShare again October 8th. We're planning a Turing run on December 16th, so stay tuned for more information. It's going to be either a run or a walkathon, I think, so we have not made up our mind, but I guess maybe both. There will be intercollegiate quiz in February, again part of the Turing Centennial events at Persistent. And again, this is the best place to know more about it. Go to this website, we keep it updated as much as we can. And again, if you want any information, you can obviously email in a quick plug about ACM. Okay, so with this, without further ado, let me talk about Neeran. So I have his CV over here, but I have known Neeran for almost 14 years now. So actually I met him at University of Minnesota, where both of us were grad students around the same time. So yeah, again, Neeran was actually, so there was the computer science aspect about him, but in the Indian community over there, he was sort of well known as the founder of Cricinfo. So I don't know how many of you know, but in those days, cricket, for people staying in US, they had to stay tuned to the matches or what's going on in India, especially on cricket. It was very difficult. There was no YouTube, there was no live satellite telecast, any of those things. And that small screen on links was to be tell us about exactly what score, who's playing what, how many scores, or what is remaining. And he was involved right from there, so he was sort of very well known in the Indian community over there as being a founding member of, it was again a very volunteer-driven organization or website, I would say, at that time. So let me talk a little bit besides that. So Dr. Neeran Karnik is a technical architect with BMC Software, working on data center systems, management, and cloud computing. He did his PhD from University of Minnesota in the area of mobile agents and security, and his work with IBM Research, Symantec, prior to BMC. Despite his best efforts at publishing technical papers and filing several patents, he is better known as a co-founder of Cricinfo, which in 1993 pioneered the sharing of critical information on the internet. Okay, over to you.
Good afternoon, everyone. I'm Neeran Karnik, and thanks to Mukund for the introduction. I'm going to be talking about Butler Lampson, who won the 1992 Turing Award. And I hope you'll forgive me if I start with a bit of a corny joke. So many of you must be familiar with this game called Cluedo, right? It's a whodunit kind of game, along the lines of Agatha Christie mysteries and so on, where there's been a murder committed in a mansion and you're supposed to figure out who was the murderer, what was the weapon they used, where was the murder committed in the mansion, etc. So I'm going to give you the answer to today's mystery. The butler did it in the laboratory with a screwdriver. Right? And why am I saying that? Apart from just being a corny joke, that's because the subject for today, Butler Lampson, is one of those relatively rare examples of Turing Award winners or famous computer scientists who actually did a lot of work in the laboratory with a screwdriver. Right? There's a different area of research altogether compared to the ones we've been hearing about in this lecture series, for example, in the past. So this kind of systems research and systems design that Lampson worked on has not led to a lot of Turing Awards and other kinds of recognition, but it is integral to our computing environments today. It is responsible for the kind of devices we are able to use today, the kind of computing power that's available today, with cloud computing and so on, adding on to the capabilities of individual devices. So we'll talk about Lampson and what he did. But before that, I'll just give a brief introduction to the systems research area and how it's different from the more traditional computer science areas that we hear about. Then I'll cover Butler Lampson's life and work. And the second half of my talk will basically be something called hints. If you're familiar with Lampson's work already, you won't need a hint to figure out what this hint is. If not, you'll get to know in the second half. And then we can take Q&A at the end, but if you have any questions in between, feel free to interrupt me and ask. So what is this systems research? And why is it different? Why is it interesting to some of us at least, in a different way than traditional computer science? So this is all about designing, building large and complex computing systems. And sometimes it's also about designing and building small and complex computing systems. It's not just about large scale, but about large complexity of the work involved. The range will go all the way from today's tablets to supercomputers, right? But it also includes other kinds of computing equipment, right? Networking, printers, and so on. Then it also includes the software. So it's not just about screwdrivers and hardware in the laboratory. To make them useful, you have to build all kinds of software, the entire stack essentially that makes the system useful. Right? So you start with the operating system, programming languages, the networking stack, file systems, distributed systems put together using these computers, etc. Right? What I'm leaving out of this list in the stack is basically application software and maybe middleware, if you want to consider that. Because that's not really systems research. Those are other interesting areas of work, but systems research typically includes the stack that comes with your machine when you buy a new machine, when you set up a new machine. And how is it different from, say, algorithm design or the other traditional areas of computer science? Right? And this, by the way, is what Lampson himself talks about. I've taken the text from one of his papers. So systems research has to deal with requirements or external interfaces of the system that are less precisely defined. So when you're asked to build an algorithm, the requirement is reasonably well defined. To take a trivial example, I need a sorted list of numbers. Given an unsorted list, I need a sorted list of numbers. And you may have non-functional requirements on top of that as well. You may have requirements dealing with performance and scale and security and so on. But these can be well specified in the case of algorithm design. When you're building a new system, a new type of computer, what is the specification there? It's very vague, right? It's going to be just that, I need a computer that has these kinds of input devices that will be able to run general purpose software that will produce output in the form of visual displays or printing or whatever it might be. So the requirements are less precise. They are more complex, and they're subject to change even during the process of development of the system that we're building. Typically, these systems research projects are long-term. any new system development takes at least 3 to 4 years before you see the first viable commercial output from a project like that. Okay? Therefore, given the long duration, requirements keep changing as well. Systems also have a lot more internal structure. They are inherently more complex, right? They have lots of moving parts. And so there are more internal interfaces between the parts of the system. So the design choices made by one team working on one part of the system can have intended or unintended consequences on other parts of the system, on the design of other parts of the system. Also, these teams tend to be large. Any of these typical projects will have large numbers of teams and people working on them. So communication between those people, collaboration between those people becomes a little more important than in the more traditional world of computer science. Also, the measure of success is kind of unclear, right? I mean, with an algorithm, you know that either it achieves its output, its functional requirement, or it doesn't. Either it achieves its non-functional requirements or it doesn't. It's relatively easy to measure and test for success. With systems, you don't really have a good measure, especially in the early days of systems, when commercial success was not such a well-defined measure of success. Right? Today, you might say that if it outsells the iPad, then it's a successful tablet, or something like that. Also, there is no such thing as a best design. You're working on something interesting, but it's not necessary that you can optimize it and produce the best possible output when you're building a new system. Right? And therefore, it's more important to avoid making terrible choices, terrible decisions that lead to a sort of failure of the system as a whole. The system not achieving its end goals because one part of the system was designed badly. And another interesting aspect is that usually the physical system doesn't even exist yet. Right? When you're building a new system of whatever kind, whether it's a computing device, a printer, or whatever, you start from scratch essentially. And so you're simultaneously, there are different teams building or co-developing the hardware and the software. Right? So how do you design and test the software if you don't have any hardware to test it on? And conversely, how do you design and test the hardware without the software being ready to demonstrate its capabilities? Right? So these are the kinds of typical challenges that we face in systems research. And today, of course, in this day and age, we may have some answers to some of these questions, like using emulators and so on. And systems are not necessarily built from scratch with no background at all. They are, in many cases, they are evolutions of existing systems. So you may be easily able to build an emulator that runs on an older version of the system and allows you to test the software or test the hardware using that kind of compatibility. Right? So with that, let me move on to Dr. Lampson himself and just an overview of what he did. And frankly, I find it kind of stunning. When I went over his profile and the work he has done, kind of envied him for the era he lived in a sense, right? Because they had this opportunity to build computing systems from scratch. Of course, the converse is that they didn't have any history to fall back upon. They didn't have a lot of previous work to fall back upon and to learn from. Right? But you'll see why I say that. So first of all, let's start with the citation that ACM gave itself for the Turing Award when they awarded him in 1992. So it's for contributions to the development of distributed personal computing environments and the technology for their implementation. That includes, so look at the range of things he's worked on, right? Workstations, networks, operating systems, programming systems, displays, security, and document publishing. All kinds of different areas in the system space. Just a short one-page kind of overview of his life, his biography, his CV, if you will. Born in 1943 in Washington, D.C. He went and got first a BA in physics at Harvard in 1964. Of course, at Harvard, they don't call it a BA, they call it an AB, which is probably some Latin version of the same thing. He went from there to UC Berkeley and joined the graduate program in physics. But pretty soon after that, he got wind of some interesting project going on called Project Genie, which we'll cover a little bit later. Literally behind closed doors at Berkeley. And it was kind of hush-hush and nobody was talking about it. But he got wind of it from some contacts. And it fascinated him, so he got involved with that project. He switched his major from physics to electrical engineering and computer science. That was the department there. And he ended up, through that project and through other things that he did at Berkeley, in the space of 3 years, ended up getting a PhD before he had turned 24, despite having basically a physics background and no computing background before that. Went on to work at 3 major organizations which are sort of well known for their systems research. Xerox PARC, probably the best known of these, and he joined it in its early days. He was there from 1971 to 84, and a lot of the work that we'll talk about today is actually came out of his work at Xerox PARC. He then went on to Digital Equipment Corporation, which specifically had a well-known lab called SRC, the Systems Research Center at DEC, which also did a lot of good work. He was there for another 11 years. And since then, he's been at Microsoft Research. Again, working mostly in the systems area, working on things like the Palladium trusted computing base and the tablet computers and things like that. Just a sampling of the systems that he worked on, and I just picked these randomly because they kind of sound like Alpha, Bravo, Charlie, Delta. But it's Alto, Bravo, Cal, and Dover. There's 4 of the systems that he built or helped to build, of different kinds altogether. And he's been decorated with all kinds of awards. Apart from the Turing Award, he's got the ACM Software Systems Award, IEEE Computer Pioneer Award, the von Neumann Award, and 3 of his papers have made it to the ACM SIGOPS Hall of Fame. SIGOPS is the Special Interest Group on Operating Systems. So 3 of the Hall of Fame papers have Lampson as a co-author. So first, and probably the most prominent example of his work, is the Xerox album. And that's a picture of what it looked like. It was a workstation, and do you notice anything interesting about that workstation? Looks like a Mac. It inspired the Mac. Maybe that's why it looks like a Mac. No, it's not so easy to make out from this picture probably, but the monitor is in portrait mode. This is a rare example of a system where the monitor was not in landscape mode. Most of our monitors, most of our machines have landscape mode monitor, but this one actually was kind of a portrait mode thing, tall monitor thing. But of course, that's not the only thing about it. The most important thing is that it was the first personal computer. The first machine built for individual personal use. Personal doesn't in this case mean home use, because that was still some time away. But it was meant for the individual use as a workstation by one person. Built in 1973 at Xerox PARC. The first computer to use the desktop metaphor. So the Mac came later, the IBM PC came after that, Windows came after that, and copied that essentially. The first computer with a mouse-driven GUI. And in fact, the legend goes that, well, maybe not legend, it's probably a true story, it's in Steve Jobs' autobiography, that he actually visited Xerox PARC, saw this thing with a mouse, and was intrigued by it, and essentially went back and asked his designers at Apple to come up with something prettier than that, but essentially performing that capability. So the Apple II and the Mac then came out with mice as their primary interaction mechanism. Where does Lampson come in? The whole thing started off in a 1972 memo written by Lampson. So he proposed this idea of a project to build a personal workstation in 1972, and it got done by 1973. So it was, it was not purely from scratch in that sense. Xerox PARC was already working on some technologies in this space, and they were able to quickly put together this personal computer. The design team itself was led by Charles Thacker, who is a relatively rare example of another systems guy who's got a Turing Award, and he got it belatedly in 2009, I think, because he's also done a phenomenal amount of work in the system space. Lampson contributed to the design and wrote the operating system. Lampson essentially single-handedly wrote the operating system for the Alto. This led to lots of accolades, of course, apart from being part of history. They won the 1984 ACM Software Systems Award. And in 2004, they won the N.E. Draper Prize, the Charles Draper Prize, which is given by the US National Academy of Engineering, sometimes referred to as the Nobel Prize in Engineering, the equivalent of that. Just like a Turing is referred to as the Nobel Prize in Computer Science. So the Alto was really influential in that respect. They didn't stop there. So Lampson then went on to lead the design team, just like Thacker had led the Alto team. He led the team for the follow-up workstations that Xerox PARC came up with. The Dorado was the first one after that, and then something called Wildflower. The Wildflower served as a prototype for a more commercially successful system called the Star. So these were all research projects, the Dorado and the Wildflower, in Xerox PARC, but Xerox was actually able to take the Wildflower and convert it into what they called an office automation system called the Star. And that was very successful for Xerox. Now for something completely different. Part of the Alto, but very different kind of project, right? So Lampson, Shimoni et al. In 1974 built the first WYSIWYG editor. First time you were able to type text into a computer and see what it would look like when it was printed. So this was also designed for the Alto, on top of the Alto. And this is just a screenshot of what it looked like. Lampson in this case is writing one of his own papers on the Bravo. And you'll see there's just a small area on the top, which is like a command area where you look at, where you can see the current status and you can type in commands. So it was like typed commands, but so there was a command area separate from the actual text or content area, which you would type in WYSIWYG fashion. This eventually led to the development of Word and other such editors. Now yet another different kind of project, right? Laser printers. So this was something pioneered by Xerox. The first laser printer ever was developed at PARC in 1969 by a team led by Gary Starkweather. This was before Lampson joined actually. But when he joined, he was able to join this project and co-design the electronics and the software for that first laser printer, which served as a prototype for a commercial model called the Xerox 9700. This is what it looked like. Big beast in those days, obviously. And then there was a follow-up model called the Dover laser printer, which was in 1976. It was specifically designed to be significantly cheaper so that they could market it to a broader market. And Lampson worked on the electronics for that laser printer as well. Yet another system, I'm kind of going not really in chronological order out here, but this is kind of going back to his days at Berkeley, where I talked about this project Genie, right? So this SDS 940 computer, SDS was Scientific Data System, that was the first general purpose time sharing system which had character by character interaction. Earlier systems, of course, the time sharing systems were around for a while by that time, but they used to be involved, as you can imagine, stacks of punch cards or paper tape that you would submit to the computer center and you would get the results back at some later point in time. This thing actually was interactive. Just a shot of what it looked like. And more interestingly, this was that project Genie that I was talking about at Berkeley, that he stumbled upon and joined as a graduate student there. He wrote parts of the operating system for this machine. And, the interesting thing is these are sort of from scratch projects, right? So they actually created several programming languages for specific purposes. There were languages around, obviously, at this time. This is the late 60s we're talking about. So there were several programming languages around, but they created special purpose ones. So he created a language called CAL, which was an interactive language for numerical computation using this machine, and QSPL for system programming, etc. So they, in order to do systems programming on the SDS 940 or on this machine, they wrote their own language. And obviously writing a language means writing the corresponding compilers or interpreters and so on that hardware. So apart from all these systems that he's built of different kinds, what else? One of his major contributions, the two-phase commit protocol for distributed transactions, was done with Howard Sturgis. And their classic paper on this, which introduced this protocol, is one of those three papers I talked about, which are in the Xerox Hall of Fame. I assume everyone is familiar with two-phase commit and how integral it is to databases. At Berkeley, he also created something called the CAL time-sharing system for an existing computer called the CDC 6400, which they had there, which pioneered all kinds of interesting concepts, shadow pages, redo logs, etc. It also was built for security purposes. It used capabilities. Now, these days we don't hear too much about capabilities, but this was one of the first sort of negative results which demonstrated that capabilities don't form a good basis for long-term security. Right? So he had some learning coming out of this, and you'll see that he was able to apply it elsewhere as well. Programming languages, I already mentioned some of the work he did, but he did a lot of work on MISA and SPL. Both were intended for systems programming. And MISA has had a lot of influence. Its process mechanism is basically what modern programming, modern thread systems are derived from. Developed a language called Cedar, which combined the virtues of MISA and Lisp. Built Euclid, which was a language explicitly designed to enable those programs to be verified automatically. Worked on Nicholas Wirth's Modular 2, extended it with some capabilities, and also worked at the bytecode machine language level. Right? For Smalltalk and MISA, etc., he developed a bytecode language as well. But we are not yet done. So we've got more to talk about what he's worked on. And like I alluded to, security was another major area in which he's made a lot of contributions. And this is just a laundry list really, but lots of interesting things here like the access matrix model, information flow control, the theory of principles. Today we commonly talk about principles going through authentication and authorization and so on. But this whole idea of principles which are not necessarily users, but could also be systems, there could also be groups of users and things like that. That model he came up with. Principles speaking for other principles, acting on behalf of other principles. He worked on Microsoft Palladium, the trusted computing base that I referred to earlier, a technique for scrubbing disk storage to securely erase data, and also some interesting angles on how economic factors can inhibit security, even when the technology is available to implement high levels of security, why it doesn't get done because of economic factors or because of other considerations like that. In networking, again, he's perhaps not as well known for networking, but he is a co-inventor on the original patent for Ethernet. Xerox actually had a patent on the Ethernet protocol on the system, and there are about 4 or 5 co-inventors on that. Lampson is one of them. He also continued that kind of work, worked on switched local area networks while he was at Tech SRC. And just to step away from systems for a while, well, not fully away from systems, but he did work on formal specification and proof while he was an adjunct faculty at MIT. He did some joint work there on specifying and proving the TCP connection establishment protocol. So it's still systems related in a sense, but what he's doing is not building systems, he's proving properties of these protocols. And he worked on Lamport's Paxos protocol as well, reliable messaging. So, given all that he's worked on, huge breadth of work, what hope do we have of summarizing his learnings or summarizing his work, deriving lessons from his work? It was a big task. Luckily for me, he's done it himself. And he's done it by writing this interesting paper called Hints for Computer System Design. And he wrote it after about 20 years of work in the systems area. It was first presented at the 9th SOSP, the Symposium on Operating System Principles, which then got printed in the SIGOPS OSR, Operating System Review, in October of 1983, and was reprinted next year in IEEE Software. It was actually the first issue of IEEE Software ever, the volume 1, number 1 of IEEE Software. By that time, he had already put in about 20 years worth of work in systems area, and it summarized the learnings from years of systems research and implementation. And the point is that this paper is still influential, although we are, in 2012 now, towards the end of 2012. What he learned from the 60s and 70s is still influential today, and I'll give just one example of that. Anyone know who that is? I've deliberately chosen a photograph that's hiding the lower half of his face. Werner Vogels, CTO of Amazon, who's probably responsible for one of the biggest systems efforts today, right? Amazon's cloud, with probably hundreds of thousands of machines in the system, able to work together and provide all kinds of software capabilities on top of that as well. So, Werner Vogels wrote in July 2012, and I'm just quoting from that. So Butler's paper shows a great mix of fundamentals and best practices from the early days of large-scale system design. And almost all of his advice has withstood the test of time, and as such, they are even more important now than in 1983. So the stuff that he laid out in 1983 is even more important because it has not been invalidated by technology changes which have occurred or market changes that have occurred over the last so many years. So this paper is organized as a series of hints. Okay, so he's careful to put in a disclaimer up front. These are not laws. These are not principles. These are hints. They're not foolproof recipes. They're not even necessarily consistent with each other. There may be some hints that conflict with each other. And they're not always appropriate in all systems projects. So in short, he's not giving any guarantees. That's his disclaimer. And it's written very interestingly. Each hint is summarized by a slogan or a one-sentence kind of summary of the hint. And it's illustrated with examples from all his systems work. So you'll see plenty of examples from, for example, the Alto file system, the Bravo editor, Interlist, Misa, all these things that he worked on. He gives detailed examples from each of these. And each of those is also preceded by an appropriate quotation from Hamlet. So he's somehow gone through Hamlet and managed to find quotations that fit the text that follows. It's a very interesting read, this paper. It's about 27 pages or so. And it's packed with all kinds of interesting information. Okay. The hints are of three kinds. So the bulk of the hints are for functionality, for ensuring that the system that you're building works and delivers the function that's intended. But there are also hints for speed. Does it do it fast enough, or what are the ways of getting it to operate fast enough? And for fault tolerance. So does it keep working in the presence of failures? And one of the prerequisites that a lot of this discussion depends on is the notion of an interface. Right? An interface that separates the implementation of some abstraction from the clients that are using that abstraction. And that's a basic principle that's valid even today in systems design. Right? You have to hide the implementation from the clients and isolate them from the details of the implementation. And he says in his paper that defining interfaces is probably the most important part of systems design. So let me start with the first one that he gives, a hint for functionality, which is do one thing at a time and do it well, which is kind of the KISS principle, right? The keep it simple, stupid principle. And he also says don't generalize because generalizations are generally wrong. So the idea is to design interfaces that deliver one well-known or well-understood capability, one well-understood function, and not try to overload them with lots of side effects and other kinds of functionality. He gives an interesting quote here. Not all the quotes are from Hamlet, by the way. He also gives a lot of quotes from other people wherever appropriate. So, such as Antoine Saint-Exupéry here. Perfection is reached not when there is no longer anything to add, but when there is no longer anything to take away. So, as applied to interface design in this case. So, interfaces should capture only the minimum essentials of an abstraction. And it must not promise more features than the implementer knows how to deliver. So, this is another interesting related point that he makes. That there may be the possibility of capturing a lot of functionality in an interface and building a complex implementation, etc. But in many cases, that becomes a complex project by itself. And not everybody is able to deliver it in a way that doesn't penalize other clients. There will be lots of different clients for your interface. Some of them will need the power, some of them will not. And you should not be penalizing the ones who don't need the power. Another interesting quote from Kelly, which is that we are faced with an insurmountable opportunity. Opportunities can also lead to problems, in a sense. He also mentions that the service should have, whatever service you're building, should have a fairly predictable cost as well. Not just an obvious function, but also a predictable cost, so that clients know what they're getting into, in a sense. and as a corollary, get it right. It's not that you simplify things down to the extent that you don't deliver the functionality that is expected by the client. And quote Einstein on that, which is that everything should be made as simple as possible, but no simpler. Okay. More corollaries to that, basically he's saying make it fast rather than general or powerful. And this is analogous to the RISC principle, right? Reduced instruction set computing, where it's better to have fast and basic operations rather than slow but powerful ones. This is because, like I just mentioned, the clients who don't need the power shouldn't have to pay more for the basic functionality. And the ones who do need the power will be able to build it as a layer on top of your basic service. Now, here's one that might not seem consistent with what we've been saying so far. It says, don't hide the power. If there is a low-level abstraction that allows something to be done quickly, higher level should not disguise this, should not bury this when they provide something more general. So all these interfaces are obviously not at one layer, right? Software is always going to be built in multiple layers. When you build a layer on top of somebody else's service, if there is an underlying service that is powerful, your interface should not obscure that power. It should allow that power to be visible to your clients as well, so that they can benefit from it. The abstraction that you provide should only conceal undesirable properties, not things like power. Here's an interesting one that proponents of functional programming will have no trouble with at all. Right? Use procedure arguments to provide flexibility in an interface. Procedure arguments are also dangerous in typical systems design, but he recommends that they should be restricted or encoded as necessary, so that clients don't have the ability to pass in arbitrary procedures to your code, into your implementation. Okay. So you can restrict them, you can encode them so that they're limited. And just gives a simple example here of an interface for listing all the elements of a set that satisfy a property. Just a filter kind of mechanism, right? So one way of building that filter might be to have a complex regular expression kind of, or a pattern language of some sort, which specifies what filter the client wants to apply on the elements of that set. But what he recommends instead is to allow the client to pass in a procedure which is the filter itself, which is the test for whether the element of the set belongs to the output, should be part of the output or not. So that your implementation remains very simple, very tight, and the clients don't have to deal with a complex language, a special purpose language. We've kind of already covered this, right? Leave it to the client. Keep the interface simple, flexible, and high performance. But the caveat is that this should be done as long as it is cheap to pass control back and forth. Because by using that RISC kind of principle, you're increasing the interaction between the client and the service. The example that he gives is the success of monitors for synchronization, because the underlying locking and signaling mechanism is extremely simple. It does very little. Different clients may have different needs for the capabilities on top, functionality on top. So they can take care of their own requirements for process scheduling, buffer allocation, resource accounting, etc. Or they could use other libraries built on top of your basic capability for that. That's why monitors have been successful for synchronization these days. The other classic example is, of course, Unix-style utilities, right? Which simply take standard input, do some processing, and dump out the output on standard out. In combination with pipes and keys and so on, you can string these together, you can compose these operations together to do what you need to do. And each particular utility is easy to understand. It does one thing well, and you can optimize it as well for that particular processing. And easy for clients to then build their own requirements in various ways. There's another example of this that I haven't put on the slides, but there's a system which shall remain unnamed, where there is a remote interface provided, which is basically the libc interface, system call interface. But it is remotable. It's like doing remote procedure calls, but these are not procedures, these are system calls. And you have the ability to execute system calls on a remote machine, after the appropriate authentication and authorization, of course. Now this seems like it fits into this principle in a sense, right? The the problem with that, of course, is that this is such a low-level interface that the interaction between the client and the server is very chatty. This is at the level of system calls. So you're opening files, you're reading from files, all of that kind of stuff. At the level of individual operations, system operations. And doing that across the network over a remote interface becomes very inexpensive, especially when the network itself can be slow or across multiple WAN links and so on. So that's the caveat that is mentioned out there. The control that goes between the client and the server, that should not be expensive. Context switching there. Another one about the continuity of interfaces, right? So it's not just important to design the right interface, but you need to keep them stable as well over time as the system evolves. The interface basically embodies assumptions that are shared by many parts of the system because there are multiple clients for your service, and so it's important to keep the interface stable. Sometimes it is inevitable that you have to make some small changes to the interface, and in simple cases, if type checking is available, just based on the number of arguments or the types of the arguments that are passed into the interface, you may be able to get away with making some small changes. Because you can detect which clients are using the old version of the interface and inform them accordingly, or throw an error accordingly, with the appropriate explanation. But it still requires programming effort to rework the integration, right? Whenever you make a change to the interface, all your clients have to make that corresponding change to the way they invoke their interface. At the same time, type checking is not going to help with semantic changes in the interface. If there's a different interpretation that you're attaching to the arguments that you're passing in, or to the value that you're returning from your procedure, that cannot be detected by a compiler. And like I said, if it's inevitable and you still have to make a change, he says keep a place to stand if you do change interfaces. Keep a place to stand basically means some kind of a compatibility package. This implements the old interface on top of the new one, so that old clients don't have to be immediately rewritten just to continue working. Provide a compatibility layer. And another example of that, or a similar example, is operating system simulators, right? Where you can simulate one set of system calls on top of another. Sigwin is an example of that. It might be used for a different purpose, not because interfaces are changing, but Sigwin allows you to use Linux or Unix POSIX calls on top of a Windows system. The advantage of this, of course, is that the development cost for building a simulator like this or a compatibility package like this is probably going to be less than the cost of fixing all your client software. So more predictable. And it can take a performance hit because of that simulation layer in between or the translation layer in between, but that's often acceptable. More hints. Treat the first thing that you're building, the first system that you're building, as a prototype. Plan to throw it away, is what he says, because you will, whether you think so or not. Right? And this is true today as well, and I'm sure most of us have experienced that. Then it talks about keeping secrets. This is one of the fundamental principles of building interfaces, right? The implementation should not be visible to the client. The client should not be allowed to make assumptions about the implementation, because otherwise you're stuck with those assumptions. In order to support those clients, you'll not be able to change your assumptions and improve your implementation in the future. This is another one which has a bit of a tension or a conflict versus the desire not to hide the power, right? So if there are assumptions about the implementation that make a dramatic difference in the performance of the client, maybe it's okay to relax this sometimes, to expose that implementation detail for the reasons of performance and things like that. Divide and conquer, another one of the famous ones, right? Reduce a problem to several easier ones so that you can tackle them one at a time. And also bite off as much as will fit, leaving the rest for the next iteration. The example he gives here is interesting. And when he says next iteration here, it is literally the next run of the program, the next iteration of a particular program. The example is of file system defragmentation on the Alto and how it uses memory. So in this case, the way it works is that goes about scanning the disk and rebuilding the index. The file system metadata basically. Now it's doing all this rebuilding of the index in memory for all the files. And as it scans across the disk, comes across page by page on the disk, it gets information about which file is stored on this page, and it builds up that map. Now this index will keep growing in memory until at some point it's possible that you run out of memory, or you don't want to use any more memory for this purpose, for defragmentation. So what the Altos file system does, and remember Lampson is the one who wrote this operating system, so he's talking about his own work here. What it does is, at that point when it hits the high watermark of memory that it wants to use, it just discards the data for half the files that it has discovered so far, and continues working on collecting data for the other half of the files. Keeps building up that index. Again, it might, in the same iteration, it might still run out of memory again. If it does, again, it discards data for half the files that he's discovered so far. Right? At the end, he's going to get some index in memory for some fraction of the total files on the disk, and he's going to write that out to disk so that those files are defragmented essentially, or their index has been rebuilt. And then he says, don't worry about it. The next time around, whenever the defragmentation happens, whenever there's idle time on the workstation, or it gets explicitly run or whatever, then you have an opportunity to work on the other fragmented files out there. Another interesting one and very practical sort of advice, which is handle the normal and the worst cases separately, because the requirements for these are different in any typical project. The normal case must be fast, and the worst case must make progress. In the worst case, you don't want deadlocks, you don't want the system to freeze, you want some progress to happen. Of course, one also expects that the normal case is normal in the sense that it happens most of the time, and the worst case happens only rarely. He gives examples of caches and hints which help the normal case. And another example from Cedar, where the garbage collector, there's a reference counting garbage collector that they've implemented in Cedar, in an implementation of Cedar language. What he does in this implementation is, normally a reference counting garbage collector would have to keep track of all the references to, all the pointers basically, and count the references to objects, and when there are no references left, you get rid of that object, right? In this case, what he says is that this implementation does not bother to count the references in local frames, the activation records of procedures. Right? Whenever the garbage collector kicks in, all the local frames are scanned sequentially to build up this information. It's not maintained on a running basis in the system. This is a significant saving because typically there aren't a lot of these local frames, stack frames, right? At any given point of time when the garbage collector is running, you won't have to do a lot of scanning because you don't have too much nesting of procedure calls typically. And most of the references are to local variables anyway. Right? So it saves a lot of time for the regular garbage collection process. Some hints for speed now. Right? The first of this is basically saying split resources in a fixed way rather than sharing them. This can be somewhat controversial today. These days we all talk about sharing of resources using cloud computing, flexible infrastructure and things like that, right? But here he's talking at a lower system level, and perhaps in the context of when this was written, probably it was more applicable than it is today. That's open to question. Generally speaking, splitting the available resources or partitioning your resources among the users, among the clients, tends to be faster in the allocation process, faster to access the resources, and more predictable as well. Right? It gives an example of using register banks versus using memory. Right? We know that compilers can allocate variables to registers rather than main memory because registers are much faster. But there is a limited number of registers available, limited set of register banks available, etc. And the process of allocating them can be pretty complex. Or trying to determine which variables to put into registers versus memory, etc. But he's saying don't worry about that. Basically, allocate to registers. Normally have multiple register banks in any processor. because they are so much faster, and they will give you the payback in terms of performance. The cost of extra resources is usually low. This is something he's saying in 1983. Okay, even in 1983, he is sort of acknowledging that these resources are relatively cheap. And what you end up doing when you do that kind of allocation, without trying to be too smart about it, without trying to be too optimal about registers, the use of your resources, is that you end up with fragmentation. You end up with some unutilized registers because your compiler was not smartly able to use them all, because you use one bank at a time, right, for one process. Nevertheless, he's saying the multiplexing overheads will often be larger than what you lose out in terms of fragmentation. So if you end up swapping in and out and so on. So that's his argument in this case. Another hint is about dynamic translation. Use dynamic translation wherever possible, from a convenient representation to one that can be quickly interpreted. So here he gives an interesting example from Smalltalk compiler. Now when he says convenient representation here, it could mean a compact representation, it could mean a representation that's easy to display or process or whatever. Right? And in this case, in his implementation of a Smalltalk compiler, he generates bytecodes, and the compiler generates bytecodes, and the virtual machine that's running the bytecodes will do a just-in-time kind of translation from the bytecode to the machine language. And there is a cache of translated bytecodes, the machine language corresponding to that. One procedure at a time, you do that translation when it is invoked, just in time. And then you reuse that because there is a cache of a limited capability, or limited size, of course. This allows you to sort of optimize on the use of, optimize on the speed of execution when the procedure gets reused multiple times because it's in the cache. And your cache replacement will take care of getting rid of procedures that are not being used frequently, and therefore the speed of execution doesn't matter so much. Another one here is about, pretty standard thing about caching. What you should do is cache answers to the expensive computations, right? So that you can reuse them and avoid recomputing the values. This is just a sort of standard definition of caching, right? Which is that you store a triple. F is a function, x is the argument passed to it, and fx is the value that it returns. Put that triple in an associative store. And he uses a very basic example, which is the processor cache, where the function f is just a fetch from memory, x is the address in memory, and the contents of that address are f of x. But of course, there's a catch here, which is that functions such as fetch are not functional in nature, right? They don't always return the same value. Obviously, it's a memory fetch. So if somebody else has done a store in between, the value has changed. Your cache is invalid. So you need to build in cache invalidation or update mechanisms in the case of non-functional f. But in general, for any kind of expensive function f, you should be caching the results to the extent that your memory resources allow you to. Here's an interesting one, a hint that says use hints. What does that mean? So in this case, hints is a technical term. It's not one of the hints that he's talking about. A hint is like a cache entry, which is the saved result of some computation, but it's not necessarily reached by an associative lookup that we just saw. And it may be wrong. It is a hint, but it's not necessarily the correct answer. Okay? So if you're using a hint and consuming a hint for some unrecoverable action, you need to first make sure that it is not wrong. So you need some kind of a fast procedure available that will tell you whether the hint is still valid or not, without having to recompute the entire value. Right? So there are situations where you are able to find a verification procedure that is much faster than the actual computation. So it allows you to reuse hints and still avoid getting into problems with actions that use that value. One example he gives here is the store and forward routing tables in ARPANET, the precursor to the internet, which is basically based on each node's opinion about its links to its neighbors, right? This is basic networking stuff these days, right? each node periodically broadcasts to its neighbors what it thinks are its best links, properties about its links. But these broadcasts can be lost, or they could be delivered out of order, which means that the tables that are getting built up using this broadcast data in each node are no more than hints. Right? They're not necessarily correct. They don't necessarily tell you the shortest path or the best path for any particular destination. But this is okay in a system like the ARPANET, because it's not taking an unrecoverable action on this basis. It is taking an action, it is routing messages based on these tables. But in the worst case, what will happen is either the message will be delivered very slowly or it will be dropped. In which case, we do have protocols at higher layers which take care of correcting these. And here's an interesting one. When in doubt, use brute force. So again, back in 1983, he's saying hardware is cheap and getting cheaper. So today we should really believe that, right? With Moore's law having had another 30 years to work on this. So brute force generally allows for simpler, cheaper, faster implementations. Right? Any brute force algorithm is generally going to be simpler to write and come up with in the first place than the clever version. And that makes the implementations tighter and faster as well. It gives an example of a chess-playing computer that uses brute force to compute not all possible moves from a particular position, because that's obviously, it has to be pruned at some point. But it's still using a computation of that nature, rather than trying to encode some sophisticated chess strategy or deep knowledge or model of chess, and then trying to generate moves to play chess. And he gives an example of chess-playing computers that have actually defeated grandmasters using brute force techniques, essentially. Some more hints on speed. Compute in the background where possible. Again, this sounds obvious today, but back in those days, it wasn't, perhaps, background processing was not so common. Especially in interactive or real-time systems, where the user is expecting a response quickly, and he gives examples of the garbage collection or email delivery. Now again, in 1983, he's talking about email delivery. It's okay to take 40 minutes to an hour to deliver email. Today, that might not be the case. But even then, you can put it into the background. You don't have to wait for an email to be completely delivered before you get back to the user. Today, of course, that's not, and the reason I say it's not possible is not just because people expect emails to be delivered immediately, but also because there are some systems that depend on two-factor authentication, for example, a code being sent by email. You can't proceed with the transaction you're executing until you get a code on email. So there may be other reasons why email kind of goes out of that list. But garbage collection is a classic example, right? You always do that in the background, rather than freezing the entire program while it happens. Use batch processing if possible. And again, this is for speed. Basically, he's arguing that doing things incrementally or applying computation incrementally usually costs more than doing it in a batch. Partly this is also for systems reasons. That devices like disks and tapes, they just work better and faster when they're accessed sequentially. Gives the example of banking systems, which use online data. So in the beginning of the day, the machine in front of a human teller is loaded with data from the system. And that data gets used, transactions are generated, and they're logged throughout the day. That data gets used during the day, but it gets thrown away at night when the batch runs. So the source of truth is what's actually stored in the batch system. After batch processing, whatever goes into the system. That's treated as the truth. But during the day, you can get away with using online data. Safety first. And this is in the context of allocating resources. He's saying it's important to avoid disaster versus being optimal. This is a point we made earlier as well, right? In the effort to try and be optimal, you might end up with a bad design. He also makes this interesting statement that a general purpose system cannot optimize the use of resources. So don't spend too much time trying too hard on that, is what he's saying. And again makes the statement hardware is cheap and getting cheaper. So let's not worry too much about optimally utilizing the hardware, is what he's saying. And the cleverness kind of works only if you have well-known predictable loads on the system. Okay. Interesting quote from Morris here, which is the nicest thing about the Alto is that it doesn't run faster at night. That's because they don't do any fancy processor scheduling algorithms. They just give a fixed share of cycles to each job. And if some of those cycles get wasted, so be it, is what they're saying. Cycles are cheap. They try not to waste them by using background processing. So if there are jobs that, if there are cycles available, they would run background jobs like garbage collection and so on at that time. And one more, shed load to control demand. Right? This is exactly what the internet does today, right? ARPANET initially started off being designed to provide guaranteed delivery, because some layer above that will take care of retransmission and so on. But that way you also send feedback to the clients that the system is in a high load state. So you get flow control in that sense. And now, just a few hints for fault tolerance that he talks about. And the first hint is not really his. He acknowledges that this is basically the classic paper by Salzer and Reed and so on. In the 1981 ICDCS, the International Conference on Distributed Computing Systems. This was a paper called The End-to-End Arguments in System Design. And the argument goes something like this. That error recovery, error detection and recovery at the application level is necessary for a reliable system. Okay? And any other error detection or recovery at lower layers is not necessary. It is strictly for performance reasons. And this might seem a little strange at first. So just to take an example to explain that. The example that he uses is file transfer, simple file transfer, copying a file across a network from machine A to machine B. Right? So machine A has a local disk on which there are some files. Machine B has a local disk. You just need to copy from A to B. Now, normally what do we expect? We have all kinds of system software, the file system software, the operating system, etc., which is doing error detection and recovery at every layer, right? We have, first of all, the file would be read from the disk in machine A into the memory in machine A. You would probably apply some kind of parity check, checksum, whatever it is, to make sure that that I/O went through correctly without any errors. Then you would do either a remote procedure call or a remote communication of some sort to machine B. At that endpoint, you would again verify that the network transmission did not cause any errors. Then you would write it to disk on machine B. Again, validate that your I/O did not create any errors in the data. All that happens. Even today it happens. The argument is that all of those are not strictly necessary, and they are not even sufficient. Because errors can happen in various ways. So the only thing that is sufficient is that after the file transfer is completed, you have to read the data back from B's disk and validate a checksum or some such mechanism against the original checksum computed by A. Right? But then why is it that we do all of these things? It's basically for performance reasons. Because we know errors can occur. If you do only the checksum validation at the end, then if any error occurs, you have to retransmit the entire file. That's the only recourse available to you. But if you do it at every stage, then you know that only a particular block was corrupted. Only a particular section of the file was corrupted. So you can retransmit a smaller portion. Right? So that's the end-to-end argument, basically saying that irrespective of what is being done by the system underneath, you have to have end-to-end error detection and recovery mechanisms. The next thing is about logging, and it defines what a log is, etc. Today we are probably very familiar with it, but logging is essential. Logging of updates ends up recording the truth about an object state. Right? Now what does that mean? Lampson is essentially treating the current state of the object in memory, let's say, as a hint. Excuse me. So he's saying the truth is basically whatever is in the logs. Whatever can be reconstructed by replaying the logs is the truth. And it's not really a hint in the sense that there isn't a cheap way to validate whether it's true or whether it's correct or not. Excuse me. It defines what a log entry should be, which is basically an update procedure, which is functional in nature, and its arguments, what values were passed to that update procedure. And the sequence of log entries can always be replayed or re-executed to reconstruct the true state. Secondly, you have to make actions atomic or restartable, right? In order for this to work. The actions that are being executed, either they should be such that failures have no effect, so they are atomic, either they're completely executed or they're never, they don't change the state at all. And the log entries that you're creating, they need to be idempotent or restartable, so that they can be partially executed any number of times if there is a failure in between, before a complete execution finally records the state of the truth in the log. So that concludes the set of hints that he goes through in the paper. This is from Hamlet, myself saying it. So, quotation from the paper. In addition to Hamlet, this is what he says. Interestingly enough, such a collection of good advice and anecdotes is rather tiresome to read, and perhaps it is best taken in small doses at bedtime. So, I didn't find it tiresome personally. I found it very interesting. But if you do, then you can take this advice of his as well. This hint, read it at bedtime in small doses. And finally, here he is saying, I can only plead that I have ignored most of these rules at least once, and nearly always regretted it. That's an excellent summary, basically, of all his learnings from all those various systems projects that he did. And it's summarized in a form that is easy to, I found it easy to read, nice to read, and very relevant today as well. What we're going to do in the second half today is, of course, hear some war stories from people who've actually been through large systems projects and see how some of these hints might have helped them, if only they had known. They did know, of course. A lot more information available about Lampson and his work. There's this very nice profile on ACM's site. Citations for the 3 papers that I talked about. So this paper, by the way, the hints paper is one of the 3 papers in the Hall of Fame. The other one I mentioned was the transactions paper, right? It was the third one as well. The two-phase commit paper was the second one I mentioned. Lampson is still active. He works at Microsoft Research. He's got his own homepage there, which will give you a lot more information about what he's up to these days, papers that he's published recently, and so on. So take a look at that. And now, any questions you might have? If anyone at the remote site has questions as well, feel free to take those. Nope. All right, thanks a lot then. Oh, there is? Okay, good. Still can't hear you. Sure.
Can you mention this given text?
I think we're trying to unmute your line. If you just hang on for a minute. In case this doesn't work, I'll be happy to take the question offline later on. Okay, we're giving you a direct phone call, so if you can just take your call, we'll get the question through that way. Okay. Apparently there are no questions. That's what he wanted to say. All right then. Thanks a lot.